Alright, so hello and welcome, howdy. I'm going to be speaking kind of lowly today again, or in this video again. We have yet another video. It's going to be random pick with weight, a LeetCode medium. Let's get it going. So, here we are. Given a zero indexed array of positive integers w, where w of I describes the weight of the ith index, you need to implement the function pickIndex, which randomly picks an index in the range 0 to w.length minus 1 inclusive and returns it. The probability of picking index I is w of I over sum of w. For example, if w equals 1 and 3, the probability of picking index 0 is 1 over 1 plus 3. Excuse me. Okay, I think I understand. So they want the index has a weight, and they're probably picking that particular index. Return 1, index equals 1. Do you return that value, or do you return the weight, or return the index? Okay. Second element, got it. So you return an index with a certain weight. Fair enough. So let's think about this for a minute before we start coding. I want to say I have seen this question already, but I didn't really have a solution for it. I just kind of pondered it. I don't think I even really pondered it, quite frankly. I think I just saw this. So let me sit and think about it for some time. What we want to do. I'm going to whisper too. As I said, I'm trying to conserve my voice somewhat. So in order to select each index with a certain probability, there are a few ways to do. Let's see how many weights do we have. There is actually a way to do this that's reasonable. 10,000 or 100,000. 100,000 weights, huh? Or no, excuse me, 10,000. And this will be called 10,000 times. Alright, so we can't do 10,000 by 10,000. There's a way to do this where you just randomly pick an integer between 0 and or between 1 and the sum, inclusive. And then you would pick, you can just subtract the weight until you get to 0, I guess. Excuse me. Is that right? So if you did 1 through 4, you could pick from 1 through 4, and you would say subtract 1, you get anything 0 or less than 0. Subtract 1, you get 1. If you subtract 1, if it's 2, 3, or 4, when you subtract 1, you still have something left over. But then you subtract 3, and you get down to 0. So if you just keep subtracting each index weight, and if you're less than or equal to 0, then that's the particular index that you need to take. That's one approach. I don't think that's the best approach, though. Let's see, is there another way we could do this? The reasons that would take 10,000 operations per check. there's another approach you could take that would take logarithmic time, where you can take the cumulative values, the cumulative weights. So you could take 1 and then 4, and then you would say, find the first value that's basically the lower bound of that array of the cumulative. So the cumulative array is monotonically increasing, I believe. Yeah, I believe it's monotonically increasing. So it would be assuming the weights, none of them are 0. I think they're all non-zero. Yeah. So it's actually monotonically increasing. It's not even non-decreasing. Or excuse me, it's not non-decreasing, it's increasing. So monotonically increasing, which means it's sorted. Which means you can perform binary searches as needed. So what you do is the number you roll, you're going to want to search for the lower bound would be the first element that's greater than or equal to, excuse me, yeah. The upper bound, I think, is the first element that's just greater than. Right. So, if you take the element, if you find the element that's greater than or equal to, and if it's equal, that's that index. But if the sum is larger, if there's none that are equal, and it's larger, then it would be that one. So I think it's just the lower bound is the one you want to take. So for like 1, 4, if you take 1 equal at 1, it's the first element. If you take 2, then greater than or equal to would be 4. Yeah, so do it that way. So we can perform a pre-processing step, and we could do it this way. And that should be sufficient for the problem. We also want a random device, as well as a Messernet twister, and finally a int distribution. Using the random library that C++ provides. So we'll preprocess. Say int I equals 0. Can actually do it this way. generator, we're going to say RD equals standard random device. You actually don't need this. I forgot about that. You can seed our generator with a Mesonite twister. And this you can actually create a new one and call it. Create a new device and seed our generator this way. And then we can say D is equal to now we're going to use A and B is 0 and B is the total. So it's really it should be 1 to the total. It's inclusive. Yeah. And then now we say which is going to be D of gen. Excuse me. D of gen. And then we say standard lower bound of cumulative weight. Feels like maybe I should use a slightly more concise name for this. And which we're going to say auto pointer. Excuse me. And then we return to get the index. We just take pointer minus the beginning pointer. Excuse me. And that should give us which index. I think that's sufficient. I think that's all we need. How are we doing on time? 13 minutes or so. Okay. Let's take example 2. Let's take some other examples. Okay. And then we want to pick index. We're going to do a whole lot of these. How many is this? This is 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Alright. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Alright, let's see if this works. Okay. I think we got it. Let's give it a shot. I don't actually know though. Oh, we got it. Sweet. Alright. There might be something better than this. I don't really know. We're going to try and run it one more time. See if we get something better. In terms of runtime, yeah, it's about as good as we got. There might be a better approach than I know. Okay, interesting. What does the discussion say? I'll go through this quickly. Cumulative frequency sum and binary search. That's what I did. Smart. O1 solution with detailed explanation. Binary search. One-liners built in. Uniform sampling. Okay. Probably we want this one. Simple and easy solution. Concise binary search. That's all I got. I didn't get better than binary search. Alright, where about the solutions? Choose linear search and binary search. Thought that all log is best, however it's not. You choose linear with smart math trick. Example, 4 boxes. Distribute weights. One of them, 2 parts in each box. Distribute like this. If weight sum is not equal to 1, normalize them first, dividing sum by all weights. Alias method. Let's see more detail. That's pretty interesting. Always a way to distribute weights like this can be proved by induction. There's always be one box with weight less than or equal to 1 over n and one greater than or equal to 1 over n. Take the first box in full and add the rest of weight for the second so that they fill the full box. Okay. One box greater than a fourth, less than a fourth. Create all boxes, generate data into 2 steps, generate box number 01. Box size, the sizes of boxes are equal. Generate point uniformly inside this box, choose the index. Law of total probability. Processing is linear, time and space is just linear. Not the easiest one to follow. The solution is keep 2 dictionaries, distribute weights more or less than 1 over n. Iterate, choose 1. Finally, we have only separate boxes. Keep boxes in the following way. List of tuples with 3 numbers, first, second. Okay. Only 1 weight, we keep its index. If you have any questions, feel free to ask. If you like the solution explanations, please vote. I do not get it. Darts, dice, coins. Wow, that's pretty wild. Yeah, I don't think this works. It's not always possible to distribute the weights to multiple boxes. Each box only has 2 options. Proof is correct, but doesn't have the restriction that each box can only hold 2 items. Once a box can hold more than 2 options, your solution breaks because stepping into the box that contains more than 2 options taking linear time. This is linear time. Okay. Well. Yeah. I didn't really verify if this is true or not. I didn't verify either of these things. Apparently you can do it in linear constant time, but I don't think so. Family efficient algorithms for sampling discrete probability distribution returns an integer values 1 through n according to some arbitrary probability distribution. Typically use n log n or linear pre-processing time. Random values can be drawn in constant time. Okay, I'd have to verify this and look it up and learn it and all that. Kinda don't want to spend the time at the moment. Maybe I should though, I don't know. Probability table, U of I, alias table. Random outcome fair dice is rule to determine index in the 2 tables. Sort that index of biased coins, then flip the outcome of the flip is choose between the result of I and K of I. Algorithm operates as follows. Uniform variate 0 to 1. I be this and Y be this. I uniformly distributed over a 1 to n and Y distributed 0 and 1. If Y is less than U of I, return I. This is the biased flip coin. Always return K of I. An alternative formulation of the probability table proposed by Marsagli et al. As the square histogram method. Use the condition x is less than V of I in the 3rd step, where V of I equals U of I plus I minus 1 over n instead of computing Y. Oh, interesting. Okay. Excuse me. Distribution may be padded with additional probabilities P of I equals 0 to increase n to a convenient value, such as the power of 2. Generate this table. Generate the table first. Initialize U of I equals n times P of I. While doing this, divide the table entries into 3 categories: over full group, under full group, and exactly full group. The U of I equals 1 corresponding to K of I will never be consulted unimportant when the value of K of I equals I is sensible. As long as not all entry tables are exactly full, repeat the following steps. Each iteration moves at least 1 entry to the exactly full category, and the last moves 2, so the procedure is guaranteed to terminate after most n minus 1 iterations. Each iteration can be done in no constant time, so the table can be set up in linear time. Voss points out that floating point rounding errors may cause the guarantee referred to in step 1 to be violated. If one category empties before the is set to 1 with negligible error in the solution. Accounting for floating points, sometimes called the Walker-Voss method or the Voss-Alias method. Alias structure is not unique. As the lookup procedure is slightly faster if y is less than u of I because k of I does not need to be consulted. One goal during table generation is to maximize the sum of the u of I. Doing this optimally turns out to be NPR, but a greedy algorithm comes reasonably close. Rob from the richest and give to the poorest, that is, at each step choose the largest u of I and the smallest u of j. Because this requires sorting, the u of I requires O of n log n time. Interesting. Interesting. Efficiency, although the alias method is very efficient in generating a uniform deviate, is itself fast. There are cases where it is far from optimal in terms of random bit usage. This is because it uses a full precision random variate each time, even when only a few random bits are needed. One case arises when the probabilities are particularly well balanced. So many u sub I equals 1 and k sub I is not needed. Generating y is a waste of time. For example, p sub 1 equals p sub 2 equals half. That third 2-bit random variate x could be used to make 32 choices, but the alias method will only generate 1. Another case arises when the probabilities are strongly unbalanced, so many u sub I is approximately 0. For example, p sub 1 equals 0.999 and p sub 2 equals 0.001. And the great majority of the time, only a few random bits are required to determine that case 1 applies. In such cases, the table method described more likely to tell us more efficient. If we make many choices with the same probability, we can, on average, require much less than one unbiased random bit. Using arithmetic coding techniques, we can approach the limit given by the binary entropy function. So, I have no idea what I'm looking at here. Really don't get it. Detailed explanation. Numerically stable version of Voss's algorithm linked to job implementation. Small C library. Implementation C++. C# implementation. Okay, interesting. Yeah, I don't really know it. I don't really get it. But basically, we're just using alias method. That's the idea. So I think that's the more efficient way. That's a lot smarter than I would be for a problem like this. I wouldn't be able to think that up offhand. What is interesting is that this counter example must not be true because yeah, okay, there you go. Yeah, the counterexample must not be true because this wouldn't be a thing if it was not true. So that's really interesting. I don't know, man. How do you let's try again. Let's try to understand it again quickly, briefly. I'm not going to memorize how to do this offhand. I guess I could just invoke this if anyone asks about it, that it can be done using the alias method. Two tables, a probability table u sub I and an alias table k sub I, to generate a random outcome. A fair dice is rolled to determine index into the two tables. So there's a probability table and an alias table, okay? Based on the probability stored at that index, a biased coin is then flipped. And the outcome of the flip is used to choose between a result of I and k sub I. So you have a dice to get an index into these two tables, and then you get a coin flip to choose a result between I and k sub I. Algorithm operates as follows. Generate a uniform random variate between 0 and 1. Okay. Let I be n times x. It's the floor of n times x. So x is some probability. N, oh, I don't know what n is though. N is, oh, I see. Okay, n is the size of, alright, I get it. So I is uniformly distributed from 1 to n. N is the size of the floor of the size, plus 1, oh, I'm sorry, I see. Floor of n times x plus 1. So it becomes some I value. And y equals n times x plus 1 minus I. Okay, I think I get it. So I is some integer, and we have n times x plus 1 minus this integer. So I guess y is also between 0 and 1 then. Now why is y that value? X is some random number between 0 and 1. So this is some random percentage of n, more or less, as not really as an integer, but as a floating point. Minus 1 minus I. So, or plus 1 minus I. Well, so really it's n of x minus the floor of n of x is kind of what this comes down to. Which means there's some probability, or some, really it's just some, not even probability, but it's a probability, but some, also some floating point number, we'll say, some real number, where this actually would be taking the, this really is another way of saying take the decimal portion, take the decimal portion of, or the remainder, remove, in other words, remove the integer portion, remove the integer portion from n times x, and that will give you y. It's not necessarily the same as x. If y is less than u of I, which I don't know what u of I is, return I. This is the biased coin flip. Okay. Otherwise, return k of I. Why this is a correct algorithm, I have no idea. And what is the idea again? The idea is to, what are we even trying to do again? We're trying to pick each index with probability proportional to the its weight. That's what it is. Trying to pick each index with probability proportional to its weight. Right. And so the way to achieve that, this is like way beyond. Like I would not. It would take me forever to think of something like this. I don't even know. Well, I probably could verify that this is true, but I don't know that offhand. Like that would probably take me a while just to verify it. Much less think it up. Much less think it up on the spot. So we're saying, okay, we pick some random number between 0 and 1, some random probability. We multiply that probability by our total, where n is the indices, the total set. So we multiply it by the indices. We take the floor, let I be the floor of that, so it's some. So yeah, so we kind of. So itchy, I'm gonna end up scratching my skin again and cutting myself. This is interesting. So normally what you would want to do is you get some probability, and you would say, if there are cumulative probabilities, you'd say, okay, depending on which quote-unquote box this falls into in this cumulative probability, that's the index we would take, and that would give you the right probabilities. What's being suggested here is to actually multiply that probability by the index, by the total number of indices, and then take the floor of that and add 1, which gives you a number, an I from 1 to n, and also, although that I would have uniformly distributed, right, which is what I is, right, something uniformly distributed from 1 to n, and y is also uniformly distributed from 0 to 1, where y is, it's not x, but it's, you take the remove the integer portion of n times x, and that gives you y, which is also uniformly distributed from 0 to 1, which is fine, yeah, that's probably just some, is that true? Actually, is that necessarily true? Now that I'm thinking about it. You could also just calculate another y that's uniformly distributed between 0 and 1, I guess. And now you say, okay, if y is less than u of I, return I. This is the biased coin flip. So for that particular I, okay, I see. So first coin flip can give you some. So you do two coin flips. The first coin flip and the second coin flip is biased, but the first coin flip gives you some index. You randomly select an index, right? The second coin flip tells you whether or not you should select that index. Otherwise, return k of I when k of I is an alias table. Okay. Which is a different value altogether. So that's interesting. So I don't know, how do you build u of I and k of I? So there's some coin flip that you make. Again, second coin flip. And what we're going to do is set up that second coin flip in such a way that if we win the coin flip, we take I. If we lose the coin flip, we take some other element. So I guess basically every index that you could pick gets paired up. I think that's the idea. Okay, interesting. Yeah, every index gets paired up with a probability to select that index. And if you fail that probability, you select a different index. So every pair, that's the alias, is every possible index has basically another value set up with it. So if you fail one, you select the other. Now the question is though, how do you set up this alias table and this probability table where this makes sense? Maybe that's the idea, that now that you've set this algorithm up in this way, it's possible to ensure that all the probabilities of these indices have the correct weights by doing basically two coin flips. By the way, this second coin flip with y, it could just be take another variable, y. It could be totally different. Doesn't actually matter. It's somewhat random what the value of this is going to be, I guess. Well, that may not be true, actually. I think. See, that's something to consider, is that depending on the value of n and x. Well, no, that is just a random variable. Yeah, because it depends on what x is. I'm actually not sure. Y might not just be another random coin flip. That might not be true. Y might need to be related to I and n and x specifically in this way. And maybe I'm wrong about that. Interesting. Okay. So u of I is going to be n times p of I. Interesting. So this is interesting because we initialize with u of I equals n times p of I. But p of I is, it might be useful to pad with p of i's to get to the table to power of 2. Okay, that's interesting. N times p of I is, but actually every probability p of I needs to be less than or equal to 1. So this will never be, I see, but greater than 1. Oh yeah, because you're multiplying by n, it could be greater than 1, I see. So we want to move everything to exactly full, I think. There's underfull and overfull groups. So move everything around until we get to exactly full categories, where u of I equals 1. Interesting. Basically, interesting. Either k of I has been initialized or u of I is equal to 1. Oh, I see. So if u of I is 1, then you always take I, but if u of I is not 1, then you have your coin flip, where you can, depending on what the value is, you'll either get k of I or I. That's really interesting. So, very interesting. Very interesting. I don't really know too much about this, but I guess there's a way to prove it. Well, there's a detailed explanation here, right? I guess this is what we should look at. Last major update was 10 years ago, huh? Wow. So this would take some time. Go into all of this. It's quite involved. It's quite involved. Yeah, okay. This is the place to go. One day, we'll come back to this, so Foss's alias method is what we're looking for. Yeah. So I think we did something like this, which is pretty good. But we want this one, we can do better. We can do better. Interesting. Okay. Sweet. That's pretty involved, this algorithm. But yeah, most of these questions have some kind of an algorithm that's not obvious to get like the optimal solution. It's usually in the discussions you can find it. So pretty good. Pretty good. But yeah, it's not beyond me, but I won't memorize that, I think. Alright, so thank you for watching. Talk to you soon. I think I'll do a few more problems. I think I want to go for another another maybe like couple hours. We'll do this. So yeah, thank you again for watching. So it's a very interesting question. There are better solutions out there. Like I said, there is an algorithm to do better. It's pretty interesting, but we won't get into that here. It seems like there's some textbooks that I probably should read. Now I'm thinking about it, like Knuth's The Art of Computer Programming books. Maybe I should read those and go through all those algorithms. There are so many algorithms out there, man. There's so many. It takes so much time to go through it all. All right. Thank you again. Take care.